The digital world is under constant threat. Malware in its various forms poses a significant risk to individuals, businesses, and governments globally. Traditional security measures often struggle to keep pace with rapidly evolving threats. Malware deep dive learning represents a significant leap forward in cybersecurity. This approach leverages the power of artificial intelligence and machine learning for advanced malware analysis. It enables more accurate identification, classification, and mitigation of threats. Deep dive learning goes beyond surface-level analysis. It delves into the intricate details of malware behavior and structure. This involves analyzing vast datasets of known and unknown malware samples. The goal is to identify patterns, anomalies, and characteristics that can be used to detect and neutralize threats. This proactive approach is crucial in today's threat landscape, where new and unknown malware emerges daily. Deep dive learning is not a single technology, but rather a collection of techniques and methodologies. This includes data collection, feature extraction, model training, detection and classification, and behavioral analysis. By combining these elements, security researchers can gain a comprehensive understanding of malware and develop effective countermeasures. This essay will explore the key components of malware deep dive learning, its applications in various security domains, and the challenges and future trends shaping this field. We will also examine ransomware as a case study, illustrating how deep dive learning is used to combat this pervasive threat. Effective malware deep dive learning relies heavily on comprehensive data. This data serves as the foundation for training AI and ML models to recognize and respond to threats. Data collection focuses on gathering various types of malware samples. These include known malware families, new variants, and even benign software for comparison. Sources for this data are diverse. Security researchers and vendors maintain extensive malware repositories. These repositories are constantly updated with new samples and analysis. Open-source threat intelligence platforms also contribute valuable data. Additionally, organizations often collect internal data from their security systems, providing real-world insights into malware encounters. Once collected, raw data needs to be processed. This is where feature extraction comes into play. This process involves identifying and extracting specific characteristics of malware that distinguish it from benign software. These features can include static features, which are characteristics derived from the malware's code without executing it. Examples include file size, header information, and specific code sequences. Dynamic features are observed when the malware is executed in a controlled environment, such as a sandbox. These features reveal the malware's behavior, including network communication patterns and interactions with the operating system. Feature extraction is crucial for training effective ML models. The quality and relevance of these features directly impact the model's accuracy in detecting and classifying malware. Model training is the heart of malware deep dive learning. This phase involves feeding the extracted features into various ML algorithms. The goal is to train these algorithms to recognize patterns and relationships within the data that indicate malicious behavior. There are various ML algorithms suitable for malware analysis. These include supervised learning, which uses labeled datasets of known malware and benign software to train the model. The model learns to distinguish between malicious and benign files based on the provided labels. Unsupervised learning uses unlabeled data. The algorithm identifies patterns and clusters within the data without prior knowledge of what constitutes malware. This is particularly useful for detecting new and unknown threats. Reinforcement learning trains the model through trial and error. The model interacts with a simulated environment and receives rewards for correct classifications and penalties for misclassifications. The choice of algorithm depends on the specific goals of the analysis, the available data, and the computational resources. Deep learning, a subset of ML that uses artificial neural networks with multiple layers, has shown great promise in malware analysis. Deep learning models can automatically learn complex features from raw data, reducing the reliance on manual feature engineering. The training process is iterative. The model's performance is continuously evaluated using test datasets. Adjustments are made to the model's parameters and architecture to improve its accuracy and efficiency. This process continues until the model achieves a satisfactory level of performance. Section 4. Detection and classification, identifying and categorizing threats. Once trained, machine learning models are deployed to detect and classify malware in real-world environments. This process involves analyzing files, network traffic, or system behavior for signs of malicious activity. The model compares the observed characteristics to the patterns it learned during training. If a match is found, the model flags the activity as potentially malicious. Detection methods can be signature-based or behavior-based. Signature-based detection relies on identifying known malware signatures, which are unique code sequences or patterns. This method is effective for detecting known threats, but struggles with new and unknown malware. Behavior-based detection focuses on identifying malicious activities or anomalies, regardless of whether the malware is known. This method is more effective against zero-day threats and polymorphic malware, which can change their signatures to evade detection. Classification goes a step further than detection. It aims to categorize the detected malware into specific families or types. This information is valuable for understanding the threat, its capabilities, and potential impact. Classification also aids in remediation efforts by providing insights into the best course of action, such as quarantine, deletion, or specific security updates. Section 5. Zero-day threat, identification and behavioral analysis, proactive defense strategies. Traditional security solutions often struggle with zero-day threats, previously unknown malware that exploits vulnerabilities before security patches are available. Deep dive learning offers a proactive approach to address this challenge. By analyzing vast data sets of both known and unknown threats, machine learning models can learn to identify patterns and anomalies that indicate malicious behavior, even in the absence of specific signatures. Behavioral analysis is a key component of zero-day threat identification. This involves monitoring how software interacts with the system and other applications. Deep dive learning models can be trained to detect suspicious behavior, such as attempts to modify system files or registry settings. This could indicate an attempt to gain control of the system or disable security measures. Unusual network communication patterns are another red flag, as malware often communicates with command and control servers or exfiltrates data. Rapid file system changes can also be indicative of ransomware, for example, which encrypts files rapidly, leading to noticeable file system activity. By detecting and flagging these behaviors, deep dive learning enables security systems to take proactive measures, such as isolating infected devices or blocking malicious network connections before significant damage occurs.